Hello, and welcome to our presentation at ICSE called Counterfactual Explanations for Models of Code. My name is Yugen. This is joint work with Ishil Dilik, Vijay Murali, and Satish Chandra. Recently, there's been a lot of work that uses machine learning for software engineering, particularly models that consume source code and provide a classification outcome. Let me give you two examples from the literature to illustrate what these models of code can do. One approach is vulnerability detection. Given a snippet of C and C++ code, the model can detect whether it contains security vulnerabilities. Another example is semantic code labeling, colloquially also referred to as method name prediction. That is a model that, given a function body in Java, can predict an appropriate name for the function. At Meta, we've deployed our own set of machine learning models that can help developers identify quality properties of their code. In the paper, we discuss three examples of machine learning models that take source code changes in so-called diffs as their input. Number one is the performance regression detection that tells developers about the likelihood of their code introducing a performance regression. Next is test plan quality assessment that is particularly trained to detect whether the test plan is ought to contain a screenshot of the application. And finally, we talk about taint propagation detection. That is a learned model that detects whether their code is introducing data flow that may propagate tainted information. So let's have a look at a concrete example. We commit changes to a function called store and display dialog, and at commit time, you're being told by the machine, red alert, this code leads to performance regression. So you may ask yourself, why does my machine learning model think this code will exhibit a performance regression? Where did it pick up its signal? This problem is even more pronounced for code changes with hundreds of lines of code. Counterfactual explanations are a technique that can help developers understand why a machine learning model thought their code exhibits certain properties. Counterfactual is a term from the causality literature and can be briefly described as an alternate world of your input, where prior circumstances are changed to assess the consequences of that change. So let's have a look at how a counterfactual input could look like in the context of our example from earlier. If we were to verbalize the counterfactual we see in this example, we would say, if you had called gen simple instead of gen handle, your code would not be classified as causing a performance regression. So counterfactual explanations for models of code do two things. Number one, they demonstrate how the model's prediction would have changed had the program been modified in a certain way. One of the advantages of counterfactual explanations compared to other feature attribution-based explanations are the clueless semantics it provides. Here is an alternative world of your input that changes the prediction, and the contrast between the original world and the counterfactual world constitutes the explanation. And we achieve this by repeatedly posing what-if questions to the model. Let's look at the problem in more formal terms. P is the original program, which is the input to the model M. Then pi is a perturbation to the program that we can apply, and G is the ground truth outcome as it will be labeled by a human user. By introducing these formal terms, we can now define what a counterfactual explanation is. Number one, the model outcome of the original program and the perturbed program are different, meaning the model flips its prediction based on the alternative input that we give them. Number two, the ground truth of the model also changes, meaning that a user looking at the original and counterfactual program would agree with the alternate label. And three, finally, the perturbation applied to the program needs to keep the alternate program that we're producing in distribution, a so-called naturalness requirement that I will go to in a second. While these were the minimal formal requirements that guide how we can generate explanations, we wanted to hear from the actual developers that will use our explanations to understand a particular model outcome. For that, we conducted a formative study with software engineers at Meta, who are experts of the respective downstream tasks we studied. At this stage, we were looking for more open-ended qualitative feedback to understand how developers would consume explanations and where we can improve. Three needs that were verbalized by the software engineers in our study stood out to us. Number one, does the counterfactual look plausible? Is this something someone would reasonably write? Number two, actionability. Is the explanation targeted enough to provide a potential recourse? Number three, consistency. Are the perturbations applied consistently throughout the input? meaning that if a perturbation is applied to one part of the source code, the same kind of perturbation should be applied to the rest to be considered consistent. I want to elaborate a bit more on the requirement of plausibility or naturalness. Let's have a look at the example from earlier, and instead of replacing one of the tokens here with an appropriate natural replacement, we replace it with just the number 5. Now, the predictive model we're using here is saying that this diff is a problem. However, the model is not saying that this expression is the root cause. What we're actually seeing here is a bad counterfactual. So how do we come to this bad counterfactual? Well, the issue is that perturbed inputs that are out of distribution have 3 properties. Number 1, their model prediction is not expected to be reliable. If you're using an input that is out of distribution for the model, any sort of outcome that we have there cannot really be trusted. And that leads to the problem that the counterfactual explanation that is generated based on this unnatural perturbation is not informative. And number 3, and this is also what we saw in the formative study, is that the user does not believe in the explanation. If someone sees an explanation like this that tells us to replace a method invocation with a number, it seems implausible, it seems like something that isn't right, and that's why the developers just didn't trust and didn't believe in this explanation. The way we deal with the naturalness/plausibility requirement is by introducing natural perturbations with masked language modeling. So imagine an indexed tokenized representation of the program P. It could look like this. We have a diff, and then we tokenize it, and we get a series of tokens that we can then feed to the machine learning model. Now, in masked language modeling, what we can do is produce natural perturbations for tokens in our input. For that, we leverage a BERT-based model that is pre-trained on millions of lines of code. We replace the token we want to perturb with a masked token. The MLM then produces a probability distribution for possible replacements of that masked token. The nice thing about MLM is it leverages both tokens before and after the mask to make the prediction. If we look at our concrete example, let's say we want to perturb the setExceptionStack method invocation. The MLM will give us a set of possible replacements from which we chose to replace it with the method invocation setMessage. This enables us to produce natural and plausible perturbations. Now that we know how we can arrive at natural perturbations for particular tokens in our input, let's have a look at the higher level loop that generates a full counterfactual explanation. We can formulate finding counterfactual explanations as an optimization problem. An exhaustive search for all combinations of tokens we need to perturb to arrive at a satisfying explanation would lead to a combinatorial explosion of our search space. That's why we use a greedy heuristic that is presented by the pseudocode you see on the right-hand side. For a number of iterations that can be passed as a hyperparameter, we expand likely perturbation targets. In every step of the loop, we expand the set of tokens to be perturbed by one more token. The way we expand the likely targets are defined by a heuristic that is implemented in the choose function. In our case, the function orders expansion candidates by the score differential retrieved by the model. That means we compare the score returned by the classifier with the score produced by the counterfactual candidate we're trying to extend. We use the score differential as a proxy of how likely it is that extending the set of tokens by another token will push the counterfactual candidate over the decision boundary of the classifier and produce a valid explanation. Now, let's have a look at this outer level loop with a concrete example. Let's remember the tokenized representation of the program P we saw before. Now, the first pass we do that we see in the iterations in our algorithm is to identify the one token explanations and prepare for extension candidates. So let's say that in this iteration, we already find a one token explanation, meaning that if we replace the setExceptionStack invocation to the invocation setMessage, we already found a perturbation that changes the prediction of the classifier. Well, what we are left with are further expansion candidates. What we do is we sort these expansion candidates by the prediction score differential. Now, in all further iterations, what we do is we iteratively expand these likely candidates by one token until the prediction changes. So if we go through another loop, what we have is if we were to perturb the setExceptionMessage invocation this expansion leads to no explanations. So we'll leave it at that. But what we found is that if we perturb the action.response body property and replace it with action.type, but also replace app.id with ID, we get an end token explanation, meaning that if we perturb these two tokens particularly, we also get an explanation, meaning that perturbing these two things will lead the prediction to change. In a set of experiments, we want to put our approach to the test. For that, we want to answer the following research questions. Number one, we want to ask engineers at Meta how useful they think counterfactual explanations are in order for them to understand why a classifier made a certain prediction. Number two, we think it's important to acknowledge that those classifiers can be wrong sometimes. So we want to understand how good our approach is helping developers in discerning the true and false positive predictions. And number three, in another experiment, we compare our approach with human rationale, meaning we have ground truth information of how a human would describe an explanation, and then we compare that ground truth with the explanation that are generated by our approach. In the first set of experiments, we asked meta engineers whether they find a certain explanation useful, and we asked them whether they can discern between the true positive from the false positive predictions. We do this by sampling 30 instances from the validation set of two models, namely performance regression detection and test plan quality prediction, and we produce counterfactual explanations for each of them. And then we asked meta software engineers, do you find this explanation useful? And also, do you know what the ground truth of that prediction is? And the results are pretty satisfying. In overall, we found that 86% of cases, people were able to properly discern between true positive and false positive instances of a prediction. And in 83.3% of cases, people found the explanation useful. Now, one particular result that we found interesting was, when was an explanation not useful for the developer? And the answer is mostly too many perturbations, meaning that if an explanation just contains too many things that have to be changed within the input, then developers did not find it useful, meaning that sparseness of an explanation is preferred. The other instance where they didn't find it useful is if the perturbation was part of a non-actionable part of the input, meaning that if they cannot really change it, or it happens in an instance of the input that is not in control by them, it wasn't really useful to them. Number two, I want to reiterate how people were able to find true from false positives based on our qualitative analysis of the responses by developers. The true positive detections reinforced the engineer's mental model, meaning that if developers were able to identify the prediction as a true positive through the explanation, it was because they built the mental model and a priori and thought, oh yeah, this is maybe what made the prediction turn out this way. The problem with that is potentially that it reinforces confirmation bias. In the cases of false positives, those were detected mostly through judging the unreasonableness of an explanation. So if they looked at the explanation and it showed them that the model provided them with an answer that of the part of the code that was not reasonable for the particular task, then they judged the model to pick up on the wrong signal. In another set of experiments, we wanted to understand how the explanations that we produce align with human rationale. And again, we sample 30 instances from a validation data set, in this case from the tame propagation detection model. And we had domain experts for that model provide human rationale for their ground truth labeling. And we see this as a proxy for human explanation. And then we asked, to what extent do these generated explanations align with the human provided rationale? What we do here is we compare our MLM-based counterfactual generation approach with another approach that uses occlusion, meaning that instead of replacing certain tokens with a natural perturbation, they just occlude the particular token and not show it in the input. And this baseline approach, SEDC, in terms of heuristics of which kind of tokens to perturb, is very similar to what our algorithm is doing. What we do in the paper, and also here on the right-hand side, we report the descriptive statistics on the number of wins. If I say win, what I mean by that is we look at the alignment of the human rationale, so what kind of tokens that humans thought were important and what alternative reality they thought might explain this, versus the explanation that is provided by both SEDC and our approach CFEX, what we call it here. And overall, our counterfactual explanation generation approach comes up with more human-like attributions more consistently over the examples. To conclude the presentation of our work, I want to go into one discussion point that came up during this research, namely the topic of robustness versus counterfactual explanations. If we look at it formally, there's not a lot of difference in both generating and assessing counterfactual explanations from adversarial examples that we find from robustness research. So how do they differ actually? So if you look at the successful perturbation for counterfactual explanation pi CF, then one thing is the same as we have in adversarial examples. The model outcome of the original program is different from the model outcome of the perturbed program. The other condition that needs to be met is the ground truth as it would be assigned by a human also differs when we apply this perturbation. So the human agrees that the ground truth has changed, so the change we're introducing is semantics altering. It provides a contrast between the original input and the counterfactual input. Now, if you look at the successful perturbation for the adversarial example, again, the model needs to change its prediction. So M of P is not equal M of the perturbation AE of P. However, the ground truth as being assigned by a human user has not changed, meaning that in an adversarial example scenario, the change we're applying is semantics preserving. We're looking for a change that if a human looks at the original input and the perturbed input, they would say that they would consider it equal, so to speak. So it's a semantics preserving change. Now, if you were to look at this on a two-dimensional plane that represents the training data, a perturbation for the counterfactual explanation stays within the realm of the distribution of a classifier and produces a perturbation that leads to a counterfactual explanation. This is also the naturalness requirement that we have seen. However, a perturbation that shows a lack of robustness goes out of distribution, but still manages to flip the model's prediction. Today, I explained to you the idea of counterfactual explanations from models of code, that given a certain piece of source code paired with a classification by a machine learning model that, for instance, tells us that this piece of code will lead to a performance regression, we ask the question why. And what we do is we introduce a counterfactual search approach with natural/plausible perturbations that repeatedly queries the black box model in a greedy guess and check fashion with masked language model perturbations. Eventually what we get is a targeted replacement within a set of tokens in the source code that gives us an alternate input that would not lead the model to think that this particular code has a certain property. You can find the approach that we have in a prototype that we open sourced on GitHub. And if you have any questions, please reach out on Twitter or by email. Thank you so much.